All right, I've recorded. So hi everyone, welcome to our another workshop for KL Mini Hack. And today we are very pleased to have Daniel from Scroll, a DevRel, to share with us about Scroll and zkEVMs. And I hope you guys enjoy this topic because this is something that I personally have been looking for. And without further ado, I will let Daniel take it away. Go for it, Daniel.
All right, thank you so much for the introduction. Yeah, so this talk is called Scaling Ethereum with Rollups and Zero Knowledge Proofs. For context, we are going to really stay at a high level, try to get some fundamentals and understanding more about what layer twos are, all these things. If you came to see an architecture deep dive into Scroll, sorry, there'll be a little bit of that, but check out YouTube videos and other places as well. But let's dive right into it. I am Daniel Helm. I lead developer relations at Scroll. And if you haven't heard of Scroll, here's what you would see if you went to our webpage. It says the native zkEVM scaling solution for Ethereum. Scroll is a zkEVM-based zk rollup on Ethereum that enables native compatibility for existing Ethereum applications and tools. So if you're not really deep in the ecosystem, that probably makes you feel a little bit like this, right? You have all this jargon. What is ZK? What is EVM? Why does Ethereum need a scaling solution at all? And so that's what we hope to address a little bit in this talk, right? We want to kind of demystify this, and I hope at the end of this talk, you'll be able to go to our homepage and be like, oh, I get it now. And if you don't get anything else out of this talk, I want you to take this away. For users and devs, Scroll is pretty much Ethereum. We'll have lots of little caveats here and there, but for most users and devs, Scroll is just like Ethereum. And what better way to see that and to experience that than a quick live demo? I think people get freaked out by the ZK stuff. They feel like it's over their head, but let's just do a live demo to show what it looks and feels like to just use Scroll, right? So if we were to go to like scroll.io, we could click join the pre-alpha testnet. And I've already connected my wallet. I've gone through the faucet. I've bridged things from layer 1 to layer 2. But once you're kind of in the Scroll ecosystem, you can use apps like our Uniswap v3 demo that we deployed. And so you can connect with your wallet. We can see what that looks like in MetaMask. I bet it's locked, but let's see if it'll pull up here. And so you can see I've connected to a Scroll L2 testnet. And just like you'd expect, I can type in a number of ETH and I could trade those for, say, USDC here, get an exchange rate and swap, and do exactly what I would do in an Ethereum. There's nothing really different here. I pay a little bit of gas. And typically I could count to like 1, 2, 3, and it's done. So we have a 4-second transaction time, which is actually feels more snappy than Ethereum. Okay, so I did my little Scroll demo here just so we can say, you've seen Scroll being used. It's not that intimidating. We're going to get down to some fundamentals, but if it feels too much, don't worry about it. So to tell the kind of story of Scroll, why Scroll, what we're building, got to start off with blockchain scalability and understanding what this problem is, why we're trying to solve for it. So we can start off looking at the promise of Ethereum. I think all this is probably pretty well-trodden territory for an Ethereum meetup, but we'll get into it. We've got a platform for decentralized applications. It's like a single network where we can share code and data. We can create all these new possibilities in code where we can kind of solve consensus problems. It's open to everyone. Anyone can join in, right? This is the promise of Ethereum. And anyone can join in, just not too many people at once, right? If we get too many users at once, we run into this issue. We run into making a swap, making an NFT trade or a mint. And we see that our estimated gas fee is in the hundreds of dollars. And we say, oh, it doesn't feel that open to me now in this moment. if you want to understand what's going on here and to better understand scalability in general, we need to look at why that happens, right? We have Ethereum blocks, and when we go to make those transactions, our token swaps, our NFT mints, what we're asking the network to do is a certain amount of work, right? The whole network as a whole is doing a bunch of work as a kind of a unified group. And so this work is measured in gas, and these transactions are put into blocks. These blocks can only do so much of this work in any one time. So the block does the work of the transactions that are going to pay the most for that work, right? So if you have so many transactions that you fill up a whole block, you got to start figuring out who gets in, who has to wait. And so this is what happens. The blocks are going to include those transactions that pay the most. So this is the kind of general idea of block space, right? We have a finite amount of work that Ethereum is going to do in a given time period. And if it fills up, fees are going to increase. So yeah, this is the simple version of the story, right? And so we're all engineers here, lots of engineers. It's a hackathon. And so we want to come up with a solution when we find an annoying problem. And paying $100 for a transaction is an annoying problem. So I think the first naive solution you can think is, okay, well, let's just make the chain do more work, right? We can do more work for each one of these blocks. Okay, well, Ethereum is a decentralized network. There's all these nodes, validators, and each one of these nodes, to make sure the network keeps going, has to do every single piece of that work, right? This block is going to do, or sorry, this node will do all the work for a transaction. This node will do all the same work for the same transaction, because they all have to come to consensus and agree on what the difference is going to be from one block to the next. And so what you're actually saying when you say make the chain do more work is not that. You're saying make every single node in the network do more work, right? Which maybe we could here and there. And really, if all the nodes are supercomputers or living in data centers, they're going to shrug their shoulders. No big deal. We can take on way more work than Ethereum does. But if you have people using Raspberry Pis, not so much, right? These smaller computers, slower internet access machines, maybe without as much hard drive space, you can only push the amount of work so far before you start pricing these participants out of the network as well. And so what happens is you have a network that used to look like this, but now a bunch of them can't participate, and it becomes much easier for nefarious actors to kind of hop in and have issues in the network. All right, there's a name for this. This is one little piece of something larger called the scalability trilemma. If you're interested in doing a deeper dive into this concept, Vitalik, I think, has a blog post from 2019 where this is introduced. He goes into depth about it. But the quick overview is this. When you have a blockchain, you get to pick two of these three things. We've got scalability, decentralized network, or a secure network, but you get to have two, right? So Bitcoin and Ethereum, traditional chains, prioritize decentralization and security, okay? When our hypothetical engineer said, well, just make the chain do more work, that's kind of the model of high transaction per second chains. That's kind of moving away from the decentralization into this kind of solution territory, which is not exactly what we want, right? So another solution we could come up with is just to say, well, okay, we can't make the existing network do more work. Let's just spin up a second network, right? And then we've got twice as much network, twice as much block space, and we're good to go. All right, back to our trusty diagram here, where we would essentially be saying, okay, we have a validator set, we have all these full nodes, all these network participants. Let's put half of them over here and half of them over there. This side will still be Ethereum, and that side can be Ethereum Prime, right? And you probably already start seeing what the problem is here. We've cut our number of validators in half, making it easier for one set to be compromised. And so the security of these things gets reduced. Not to mention, you have to also now figure out how to bridge that divide and everything else. Okay, so here, we've gone in the route of a multi-chain ecosystem. And again, we're trying to move towards scalability, but at the same time, we're making sacrifices in our security and maybe in our decentralization. So how are we going to fix this? Well, this has been a subject of research for many years. This is not a new issue, but layer 2s and rollups have kind of emerged as the go-to way for solving the scalability issue. And so we saw our network before. We can label this as Ethereum, and this whole thing we can consider like the Ethereum network here. And we also mentioned that, Ethereum is doing a big chunk of work, right? Every block, it's going to process these transactions. The transactions will have logic in them. There's programs running on this machine, but it's doing this big chunk of work. And so if we start imagining the different pieces of this big block of work that gets done, this could be the NFT mint. This could be the token swap. This could be a flash loan. Who knows? But what if we did a thought experiment here and we took one chunk of the work and we dedicated that chunk just to making sure that some other new network doesn't break its rules, right? We have a whole protocol, blockchain, whatever else, off of Ethereum. We can call this an off-chain protocol, but we dedicate a piece of Ethereum's work to making sure that that protocol isn't lying, cheating, and stealing, that it's following the rules that it's set out to do. And so this is the idea of how we can use Ethereum to secure off-chain protocols. And so layer 2s is what these can get called, and they exist as their own off-chain protocol, but use layer 1 as an important piece of the architecture, right? People say that the layer 2 is deployed on top of the layer 1, but it's like this just separate network that gets tethered in some way to the base layer, right? And here we're talking about Ethereum, so I'll probably just start saying Ethereum instead of layer 1. When we talk about a rollup, we're specifically using our layer 1 to make certain types of security guarantees, right? So layer 2 generically could do whatever it wants, but a rollup is going to make security guarantees happen on that Ethereum work, right? The work that Ethereum is going to do is going to help our rollup do things like ordering. It's going to provide things like data availability. It's going to help with censorship resistance. It's going to help with correctness of the protocol. And so that's what is really exciting about rollups. And we're going to dive into this a little bit more as well. And so the language that gets used for this is that, a rollup on Ethereum inherits the security of Ethereum. Rollups, Ethereum allows rollups to just kind of lock down the security piece because Ethereum's got it locked down so that it can focus on the scalability things. So again, back to our fun trilemma issue here, we've got Ethereum locking down our secure angle so that now the solutions of make a new network or make the chain do more work, these start to make more sense, right? Because we've got the security locked down and we can move towards scalability here. If you've been around Ethereum very long or at all, you have heard of these layer 2 networks, right? You have all sorts of them, all kind of competing or cooperating to increase the capacity of Ethereum. And some of them are, totally different than Ethereum, but still use Ethereum to try to get this security element. So as long as we're playing protocol engineer here and coming up with new ideas, I'll come up with a totally unbiased way to describe what Scroll does. We could ask ourselves, what should our rollup do, right? We're going to make a rollup. It's going to help scale Ethereum. It's going to provide more block space. But what should be what we focus on? Well, we can look at Ethereum and say, what makes it so great, right? Well, it's great because it has this incredible ecosystem. We've got amazing tooling, educational resources, user communities, smart contracts, pre-existing projects. Like Ethereum's got it's a special place, and we love Ethereum. That's why we're building on Ethereum in the first place. And so for our rollup, why would we stop at just inheriting security? Why wouldn't we also want to inherit the tooling, the educational resources, the users, the communities, the smart contract code? And so that's kind of what we're looking at, right? Where we can, we should make our rollup just behave as closely as possible to the Ethereum virtual machine. And the EVM is that which does the work in the network. There's all this other stuff about the communications and everything else. But the apps that we're writing and the smart contract code, that's all going through the EVM. And so that's really the core of the network, that the seed that we can reuse in order to maintain all this incredible ecosystem benefits. And so, no surprise, I've described Scroll's approach to building on Ethereum and building a rollup, okay? So before, just to kind of bring it home, I talked about this big chunk of work that Ethereum does. We're going to devote some of this block space to making sure that a new network doesn't break the rules. Well, more specifically, we can look at how this works with rollups. And you might have heard of projects like Optimism or Arbitrum. And what they do is they are called optimistic rollups. And they use something called fraud proofs. And the fraud proof is kind of this mechanism for someone to say, like, no, the network broke a rule. Now I need Ethereum layer 1 to kind of be the judge of whether or not the off-chain protocol actually broke this rule or not. And they're kind of, the process is lengthy because the idea is that anyone can get involved here. We're not going to focus on optimistic rollups, but just to kind of give context, that is one option you can take. But the title of this talk talked about zk rollups, and that's what Scroll is building. And so we need to figure out, like, what's the security mechanism that actually makes this all work, right? Like, what's happening on the layer 1 where we can make this claim that we can have a whole new Ethereum and still have it secure? And to start understanding that, we're going to have to move into zero-knowledge proofs. Now, zero-knowledge proofs is a big terrain with lots and lots of use cases. You're going to hear the most kind of like simplified and biased version of this, where math is not welcome. So if that's what you're hankering for, there's lots of great educational resources and more coming out all the time. And maybe in the question section, I can help push you towards some of those. But let's start off with a thought experiment, especially for folks that are new to zk. Let's try to break it down. Again, I love this big box of work. We don't have to label it. We don't really know what it is, but we have a big chunk of work to do. And this is a lot of work. And it's going to be done over some sort of like data, some sort of input to the system. And this is so big of work that we need like a whole data center of supercomputers to do this. And so here's the thought experiment. What if we had a magic wand and we could create a receipt, and we could call this receipt a proof. And what this receipt is it's like not a log of the work. It's not something to do so you can redo all the work. It's just a way for you to kind of be able to have something somewhere else, a smaller computer, just be able to verify that all of this work was done correctly, that all of this work, we don't trust this big supercomputer, but we just want to know that at the end of the day, what came out of all that work is correct. And we want to say, yep, seems good, seems right. The magic wand here is here because this seems kind of magical, right? A small computer verifying a whole network worth of computers. Well, if you have heard of zk proofs and are aware of zero knowledge, the magic is going to take us in a time machine, but not forwards, but backwards to the 90s and even the late 80s, when we had papers like this. We had checking computations in polyrhythmic time, polylogarithmic time. It's a mouthful. But, you know, at the time, there was research and writing going on, doing cool stuff like coming up with a setup where a single reliable PC can monitor the operation of a herd of supercomputers working with extremely powerful but unreliable software and untested hardware, right? So this is kind of that idea. We can have a very simple machine that is able to, you check the receipt of something that we don't trust, that's unreliable, that's way more complex, but at the end of the day, because of the beauty of mathematics, we can check these things. So fast forward to today, this has changed a lot. There have been a crazy amount of developments in this field, mostly pushed by blockchain applications. And, you know, I think to look at the scroll version here, let's kind of erase away the supercomputer and the small computer, but keep this idea of the proof and the proof verifier. So for our work here, what if our work was literally just the Ethereum virtual machine, right? All the Ethereum virtual machine is just a program run by computers. So there's, you know, there are special things about it, but it's not all that unique or special, right? And instead of just our data or input, we could bring in things like new transactions or past blockchain state. Instead of our herd of supercomputers, we could have a brand new off-chain protocol. We could have its own blockchain with its own computers processing all these transactions. And then when it created the receipt, instead of passing it to our Raspberry Pi, we pass that on to Ethereum itself, right? Ethereum can run, it is a simple computer, that is what it can do. And what it can do is allocate a little bit of its work to verifying the proof and saying, yes, all of the transactions, swaps, everything else, I don't have to redo that as Ethereum. I can just double check that they were done correctly. And so that's the magic that kind of is happening under the hood here. All right, big caveat. In this past bit, I have our input here, and these are all very public inputs, right? Everyone can see the transactions being submitted. But zero-knowledge proofs can also use private inputs that don't ever have to get passed along to the verifier. If you see things about privacy protocols and privacy zkEVMs, they're using this aspect of ZK proofs. But for what we're doing, kind of emulating the EVM, a zkEVM does not need those private inputs. And so, yeah, we are using ZK proofs, zero-knowledge proofs, specifically for this succinctness quality, this way of kind of smashing down the proof of the computation and the representation that everything happened according to plan. All right, so coming back full circle, we've got our rollup. It's a ZK rollup, and what we are committing is a ZK proof, and that proof, or rather the work being done on Ethereum is a program here, actually. It's a smart contract that is verifying the proof from our zkEVM. Like, that is the computation being done on the L1. Okay, so we're getting through the parts. We've talked about all sorts of things, right? We've seen the problem with scalability. We've seen layer twos. I did the world's fastest intro to zero-knowledge proofs. Now let's get into Scroll. Let's try to understand what we're building, what we're thinking about. And to lead off the kind of Scroll conversation, I'm going to give some value props for Scroll. Why Scroll? Why use it? Why build on it? So the main thing that makes Scroll great, in my opinion, as a developer relations person, is the developer experience. How we have designed this secondary network, this zkEVM rollup, is that the code on that network is bytecode equivalent with Ethereum's EVM, which means if you write a smart contract, that bytecode is going to be the same for mainnet as it is on our rollup. If you're used to using, tooling, hard hat, Foundry, your favorite wallets, all of those things, you can kind of reuse them just fine on Scroll, and you can even copy paste, your favorite Solidity contracts. And you can follow your favorite tutorials and just deploy to Scroll instead, which is a great thing for a hackathon. All right, so why else? Well, we get, compared to layer one, we have a lot more throughput, right? We are creating more secure block space for Ethereum, which is going to save users gas fees, right? We want to bring down these costs so that we can onboard the next generation of users and developers into the Ethereum ecosystem. And lastly, one exciting thing is because of this architecture, we actually can reduce the time between blocks by quite a bit. On a good day, we've got 3-second block times, and that's what we are shooting for at normal operation, which means that when you're using web apps, it's not like I make a transaction on my app and I twiddle my thumb for 10 seconds. I only twiddle my thumbs for 3 seconds, which is not quite as bad. It can really make the difference between an app feeling responsive and usable or not. Another, I think, important aspect of why Scroll is alignment. We really are trying to build on Ethereum's vision, build in coordination with the Ethereum community, with the EF and some of their research teams. And yeah, I don't need to go too far into that. So I want to give a few more diagrams of what Scroll is kind of doing, get a little bit less vague and kind of talk about it as a network. But this is, I think, really the most you need to know as a developer, right? We have Scroll as our layer 2 down here. Transactions are going to come into a node. Most likely, they're going to come into Scroll's public RPC, but we also have some infrastructure providers and partners that have RPC nodes you can submit transactions to. And it's going to interact with a smart contract on Ethereum, right? We said we're going to commit data, like these transactions will actually get written back to Ethereum, and then we're going to generate these proofs, and those are also going to go into the smart contract. This vastly simplifies the architecture. This is actually a better representation, and I'll speak through it quickly, but again, if you really want to do a deep dive, go look for some videos from our founders. There's some from DevCon and other times that get more into it. But a transaction comes into the sequencer, and the sequencer is going to do a few things. There's the executor, which is essentially Geth, if you're familiar with that Go Ethereum client. And it's just going to take and process these transactions, and it will output the what's called the trace. And so the work that's being done by the transactions coming into the network, that kind of record of all the things that happen when that transaction gets processed, that record gets passed to something called the coordinator, who then will choose a prover in our decentralized prover network to take that record and pass it into their zkEVM. This is our magical proof generator that will get passed back to a coordinator, and that coordinator will commit that to the L1 in our rollup contract. Some other things are going on at the same time. We've got our transactions as they come in getting passed to a relayer, and those get kind of committed over here in the bridge contract as well. We have a watcher in our sequencer that is watching for assets to come into our L1, because you got to bring stuff off of the L1 into the L2, and so things will get locked up in here and then regenerated here. So there's a lot more going on and a lot of things to coordinate and considerations to make, and but we're not going to go into the architecture here. I just want to give you a taste of all the things kind of behind the scenes. And then to kind of see what it looks like as a block by block version, I think seeing it happen through time is really helpful. So we have another view here where we have Scroll as our L2, and it's, spitting out blocks every 3 seconds. And these blocks will actually get kind of batched together. And once a certain amount of gas is used across those blocks, the transactions will be committed to the L1. So the my NFT mint and my token swap, that data of me doing that will actually get written onto Ethereum layer 1. Just the data, it won't get executed there, but the data will be always available back on the Ethereum mainnet. Then later in time, once we've gotten our decentralized prover network to run the zk proof, maybe a few Ethereum blocks later, then the same batch will have a proof committed to the L1. So let's we'll see what that looks like step by step as well, because I think it's kind of interesting. But we can think of our L2 blocks as having 3 different statuses. We have pre-committed, meaning that those transactions in the block have been taken on by our sequencer, and they're true on our L2 chain, but they haven't actually been committed to our L1 yet. And so, it's hard to, we don't really have that security of Ethereum quite yet for those transactions. Then once those transactions get committed to on the layer 1, once they've been written to that smart contract, we call those blocks committed. And then we only consider them finalized and really fully secure once we have a proof that has been posted back on the L1. So that's going to be a little bit longer while the decentralized prover network is working through the zero knowledge proofs. And in actuality, that time that it takes to generate those proofs, it varies, but I think as of today, there's always kind of improvements coming out, but I think as of today, it's can range between 5 and 20 minutes for those proofs to be generated, which can sound like a long time, but compared to optimistic rollups, you've got to wait about 2 weeks for that finalization to happen. So, okay, so let's see what this looks like step by step. We have a block created by our sequencer. Its data gets committed to our L1 rollup contract. And so now it went from a pre-committed block to being a committed block. That committed block gets passed to a coordinator, and it gets then sent off to prover number 1 for proof generation. T1 here means trace, the trace of this. Okay, so next we have block 2. It gets committed on chain. We get the trace. It gets passed off to prover number 2. And, prover number 1 is still doing proof generation for batch 1, but it's okay. It doesn't matter. These things can happen fully in parallel because we know the sequence of events here on the rollup contract. And, prover 2 could finish generation before prover 1. It doesn't actually matter. All right, so now we've got batch 3, we've got batch 4, and then something maybe more interesting happens. All of these provers have finished their proof for their batch of blocks here. And then we can actually aggregate these proofs. So instead of making the Ethereum network verify 1, 2, 3 proofs, we can actually then throw all of these into another proof. We have proofs on proofs. And so we pass these to another zero knowledge proof called our aggregate proof generation circuit. And once that is finished, that is what's going to get committed on chain, and the smart contract will verify that that is correct, or it will reject it. And if it rejects it, bad, network wrong, we've got all sorts of issues, but it will accept it because we've also guaranteed that we're not going to break the rules here. And so what we have is now we've verified that smart contract. So batch 1, 2, and 3 here have become finalized, right? Number 4 still's got a proof generation and verification to go, but we can consider all of these finalized. And so that's what it looks like for the Scroll network to be doing that. If you want to explore this more, we have something called a Rollup Explorer. We have chain explorers just like you would see on Ethereum or somewhere else, but we also have this Rollup Explorer, which lets you look at what the last pre-committed block is, committed block, and last finalized block. And you can kind of track these things in real time. And so you can see, we have an L2 block number, and it's been committed on to the L1, but it hasn't been finalized yet. And so we can see the commitment hash on L1, but it hasn't had a proof generated, so we don't have a finalization hash on L1. And then this would be, this is, I guess, proofs that are somewhere around 18 minutes at this point in time. And so we have this block being finalized and committed at this hash on the L1. And so we've changed states here. Okay, so we went deep down into it. If you're not super comfortable thinking about blocks and transactions and commitments, that's fine. Let's come back to where we started. For users and devs, Scroll is pretty much Ethereum, but faster, cheaper, and hopefully more accessible to more users at the same time. So that's the goal. That's what we're building for. But right now, we're not on mainnet. So we are still in our pre-alpha testnet, but you can use it. It's open. So just like you saw me go to scroll.io and click the test the pre-alpha testnet, you can go and do that as well. Really, all tooling should work. Just changing your RPC URL is what it really takes. In this pre-alpha testnet, we're not using Ethereum for it, and we're not even using a public Ethereum L1 testnet. We're running our own L1 testnet until our alpha release, which is going to be soon. No dates, but soon. If you're interested in trying this out from kind of the user perspective, check out scroll.io/pre-alpha, where, like I showed before, there's buttons to set up your MetaMask wallet, get funds from our faucet and bridge those over. We have a user guide that will walk you through those steps as well at guide.scroll.io. But much more interesting to me is some of our developer resources. So we have developer docs at that same location. So guide.scroll.io/developers, or just click around. You'll see a quick start guide for Hard Hat, Foundry, Scaffold ETH, and lots of other tooling. Also a deployment tutorial if you just want to clone a repo and get going. If you want to learn more about our architecture, check out scroll.io/blog. And if you want to join our Discord community, check out discord.gg/scroll. Okay, at this point in time, I kind of planned a quick deployment workshop. I don't know the best way if in this format we are taking questions or anything, but I also don't want people to have questions, but also want to jump because I get kind of deep into code or anything. So let me check the chat at least and see if we have any questions.
Seems like we are good on questions. I think you can just go for it. And at the end, we'll have like a Q&A session and also like a small fireside chat. I think that would be nice.
Perfect. All right. So let's dive into the workshop piece. It's going to be quick, right? Because I don't need to teach anyone Solidity here. We're just showing how to like get Scroll going. So what I'm going to do is clone an existing Scaffold ETH project. If you haven't seen Scaffold ETH, it's amazing as a way to get hacking on Ethereum quickly. We're going to adjust the deployment settings to use the Scroll pre-alpha testnet. We're going to use the developer quick start to walk us through that. We're going to adjust the front end because we have a web app that goes along with our project. It's not just the smart contract. And those will use the testnet as well. And then we're going to have to do a few things like fund our deployment wallet, deploy the contracts, debug an issue that we're going to run into, and then try out the project. So let's dive right into it. This is the fun part. Okay, so we're going to go to guide.scroll.io to start us off here. And if we come down, we have our developers section. And this will kind of tell us all about building on Scroll, but we're going to go to the developer quick start. And we don't need to read this because I'm going to tell us how to acquire testnet ether. There's a faucet, no big deal. But let's go to Scaffold ETH on our instructions here. And this is what we're going to use to kind of guide us through how to do this deployment. So to get started with scaffold ETH, we're going to go to the scaffold ETH repo and we're going to clone it. And I'm going to kind of fake it. I've already cloned it and installed the dependencies because JavaScript is slow. But what you'll want to do is type your git clone command and select it into a certain folder. Actually, this is the base repo. Let's select a specific project. On Scaffold ETH, what's really cool is all these hackers have different branches of the repo that do all sorts of crazy things and all sorts of experimentation, cool smart contracts you can check out. But there's a real simple one called Dice Game, and that's what we're going to start off with here. Okay, so what we would do is clone our repo into something like Dice Game. I'm going to call this Dice Game fake because I'm going to cancel the command, and then we're going to act like I did it into Dice Game. And so now we have our repo here. And then we'll want to select this specific branch of the repo. So I'll say git checkout Dice Game. And then we're going to run yarn install. And this is going to install all of our dependencies. And I've already done it ahead of time because, like I said, it can take a long time otherwise. So now we have all these dependencies installed. And if you haven't used Scaffold ETH, it's really cool. You can open up 3 different terminals, one to run a local chain, one to be building your front end, and one for deploying your back end or deploying your smart contract to the local hard hat chain. But we're not going to have to mess with all that because we're just going to deploy straight to scroll because we're wild like that. So what I would like to do is come back to our instructions here and also open up our terminal to take a look at our code. And so the first thing when we're configuring Scaffold ETH is that we need to configure hard hat. I imagine I probably need to make this a tiny bit bigger for the screens here. And it says that we'll need to go into packages, hard hat, and our hard hat configuration file. And what we need to do is just add this scroll network as a network that's available to hard hat. And so we're going to copy paste this. It's bigger for everyone. We're going to come back to that. So we have our networks. We see localhost here. And now we've added scroll pre-alpha. This is our arbitrary name. We can call it whatever we want. We want to point it to the scroll layer 2 RPC node. This is a really cool function here in hard hat that lets us use kind of a hard hat wallet that we'll see in just a second. The other thing we need to do in this area, as mentioned here, is we want to set the default network for hard hat to be using scroll pre-alpha. Cool. And I will save that. We're going to need to fund that wallet here in just a second, but let's go ahead and already configure our front end as well. What we can do is go to packages, React app, and we are going to go to the source folder. And as mentioned here, we have constants.js, which defines all of our networks. And so we're going to be able to open that up and copy paste the scroll pre-alpha network. And here again, we're giving it a name. We're saying what the RPC is, where to find the block explorer, defining the chain ID, and even giving it the scroll brand color. Fun stuff. All right, and then the last thing we need to do to get our front end ready to go is go into our app.jsx and define, hey, we want the default network to be scroll pre-alpha. So let's open that up. Great. And so we, for the most part, should be good to go. So let's see what happens if we try to just deploy this as is. We can say yarn deploy. It's going to try to do this. In the interest of time and leaving time for questions, I'm going to tell you that it's not going to work because we have not created a wallet to deploy this from, right? To deploy this, we need funds in a wallet. So we can run yarn generate, and it's going to throw a bunch of warnings, but it's also going to create a public address here. And if we type in yarn account, it actually does this cool thing where we get a QR code for our wallet and the account where it's located at. And it'll start checking actually a bunch of our balances in different networks. And so scroll pre-alpha, we don't have any balance yet, but I've already pulled some from the faucet, and I've already bridged those to the L2. And so I can send that address some testnet ETH. I don't think I mentioned this in the talk. Says TS ETH, but at mainnet, this is just going to be bridged Ethereum. It's not some special scroll token or something where all this transaction is happening in the same currency as the layer one, which is Ether, right? So here we go. We should be sending funds to that account. And that looks like it was successful. And so if we run our command again, when we say yarn account, now our scroll balance should be higher. So now we actually have a proper balance in that account. Great. So now let's try this again. I also forgot earlier, when we go to yarn deploy, we need to define our network. And we're going to say scroll pre-alpha. And so now our smart contract is compiling. It's all going. It's finished compiling. We're deploying our contract. We've made a transaction. And then we get errors. We get all sorts of errors. Let's see what's going wrong. It says error processing. An Etherscan endpoint could not be found for this network. Okay, so we're an early test net. We don't have Etherscan. We actually have something called Block Scout. And so if you're wanting to explore the network, we've got an L2 block explorer you can check out. It works very similar to Etherscan, but it's not the same. But what we do need to do is actually go into this file, packages, hard hat deploy. And then this is the kind of script that is our kind of default script for deploying our contract. And there's a bit down here that, basically does stuff with Etherscan. And we could be elegant about it and say, don't do it for this network, but we're just going to totally drop it and try to deploy again. So let's clear this, run our deployment again. And I think actually technically it deployed earlier, but those errors sure were nasty. So great. We've published our contracts. We're good to go. I guess we've deployed our contracts. Maybe this is acting like we interacted with Etherscan, but we didn't. Okay. Anyways, the next thing we would want to do is get our front end going. We could deploy this online, but I'll just run it locally. Remember, we adjusted our front end so that it would point to scroll pre-alpha testnet. So I can type in yarn start. We're going to wait a while for this to get going, but it's going to end up going at localhost 3000. And now we get to wait on create React app to do all of its fun stuff, which can sometimes take some time. Could have kicked it off maybe a bit earlier here. But yeah, so if you haven't seen Scaffold ETH's front ends, they're really cool. What we'll end up seeing here in a second is all sorts of modules that look into our smart contract in different ways, and really simple UIs that make it really clear how to interact with them. When you're developing on localhost, you have like faucets and all sorts of things to be able to quickly hack things together and test them out. But now that we've switched over to pointing at the scroll pre-alpha testnet, we'll see a few less of those, because we won't just use a wallet that lives in the browser. We'll use MetaMask specifically for our wallet to interact. Sometimes compiling code, like running code, feels slow. It feels 3 times as slow when you're on a live stream, but maybe while that keeps kicking off, I mentioned before the Rollup Explorer. If you go to guide.scroll.io, we've got links to our block explorers, our Rollup Explorer, the deployment tutorial I mentioned, different smart contracts you can be interacting with that are already deployed to our testnet. So we've got the bridge, different tokens, Uniswap v3 contracts, things like wrapped Ethereum. And all of those are available to jump on and get started as a developer. So this is odd. I don't know why it's taking so long. I'm nervous to try to cancel it at this point. Oh, here we go. Beautiful. Here's now our Scaffold ETH front end, where I'll log out here. It's going to ask me to connect my MetaMask. I've already connected, but we can see I'm on the scroll L2, where I have some testnet Ether already. And I can interact with my roll the dice contract here. And just like on Ethereum or any other testnet, be interacting with those things without changing any tooling except for pointing at a new RPC. And you'll notice, these block times are nice and quick, and the gas is kind of fake because it's a test net, but that'll be nice as well. So that's what this looks like. And I could poke around in here. Maybe I could just, one last little thing, pull up the smart contract on BlockScan here. And we can see it was deployed, and I've called it twice, and the usual Ethereum smart contract stuff. I don't need to spend any more time on it. So thanks for amusing me while I go through that. So I think that's it for the workshop. Let me know if we have questions or anything else.
Thank you, Daniel. I think that is a very, very great talk, and we walked through Scroll from A to literally Z, from how it works to how to deploy on Scroll, and I have never seen such a great talk, and I think that's fantastic. I think everyone who watches this in the future will definitely benefit from it. Thank you so much, Daniel, for doing that.
Yeah.
I don't
course.
know if you have time. Do you think you have a couple, like maybe 10 minutes to go through like some of the fireside chat so that people get to know you in person, get to know Scroll, and get to also ask some questions? Because from my experience, people normally ask questions after the first question has been asked. So I'm doing everyone an honor.
Yeah, let's make it happen.
Let's go. Thank you so much, Daniel. So, okay, just to get to know a bit of yourself, how do you get into the space and why Scroll?
Yeah, so I came into the space as a mercenary miner. It was 2016, and I had been doing video production. Heard about this stuff called mining, and I was like, "Yeah, I've got a GPU sitting around. I'll test this out." And I actually read, a very older version of the Ethereum website around then, and started mining Ethereum, but didn't get it. I didn't get it at all, and I was trying to like click around and try to like, what is this thing that I'm like actually producing money-ish out of? And I think the reading about the DAO before the DAO hack and like throwing some money at the DAO was kind of where I first started getting it. I was like, okay, we can do these cool coordination things that were not possible outside of this context before it. And I think that's when my imagination kind of got caught. Fast forward a few years, I had been like still a hobbyist outside of the space in terms of working full time. I went back to computer science school for money reasons. I ended up going to art school, and I thought I was going to be teaching art students how to code when I graduated with my master's. And COVID hit, and my teaching position I had been offered kind of like disappeared. And so I was job searching for a little bit, freelancing, doing development work. And after a little while, I was like, oh, wait, this space that I've been like a hobbyist in for 4 years at this point, like people make a living there. They like actually just do this work. And I actually ended up finding a developer relations job at a company called Skynet, which is in like the Saya decentralized storage ecosystem. And that was also one of my first projects in the space to discover back in like 2016. So it really came full circle and was there for a few years. And when Skynet as a company shut down, I knew I wanted to move into Ethereum full time, and knew I wanted to be in infrastructure. Had been hearing about zk stuff, but hadn't quite got my head around it yet. And the more I researched Scroll, the more I got excited about their approach. And eventually I just kind of bothered them until they hired me as their first DevRel. And so now we're building up a really exciting DevRel team here at Scroll. So
that's great to hear. I always believe that probably is some sort like a teacher, where you're teaching the committee on how to like code, like what you did just now, which is amazing. So definitely, you're utilizing your teaching abilities and in the Ethereum ecosystem. So that's great.
Thanks.
So okay, well, as expected, there are a couple of questions now. There's this one by Wei Ken Chu. He asks, who maintains the Scroll protocol?
That's a good question. So there's lots of pieces to like, I guess, the protocol, but if you're talking about like the infrastructure, the computers running Scroll right now, Scroll does. So Scroll is a company that exists beyond the protocol that is being built. And so we are not to that decentralized goal yet. We don't have a decentralized prover network. It's still centralized, and all the provers are run on giant machines with GPUs that we run. We're getting there. It is on the roadmap, but right now, the most an outsider outside of Scroll can participate in the network is at the node level, and so you can be a peer and run a full node with our sequencer. But even that, we're trying to keep limited to partners, just because we're still pushing out updates so fast, and we don't want to give infrastructure participants a bad experience, right? So we're trying to make sure that things get more stable before we start trying to invite in more participants in that way. But if you're talking about like the code and everything else, all open sourced. Check out github.com/scrolltech. And the zkEVM pieces are built in collaboration. It was originally actually a project. I mean, it still is a project by the Ethereum Foundation's Privacy and Scaling Explorations team, sometimes called the PSE. And so, like, if you look at their repo for their zkEVM, I think probably half of the contributors there are from Scroll. So we really take seriously this goal of making sure that this is a collaborative effort to build something that, is in line with the Ethereum roadmap and not some sort of distraction or competition against it.
Thank you, Daniel, for the answer. There's another one that's not in the chat, but it was being asked, passed to me to ask the Scroll team. It's about the difference between zkEVM. So we are aware that in the market there are a couple, I think 3 or 4, Scroll, Tycho. I think Tycho is zkEVM, if I'm not mistaken. Polygon Hermes and zkSync. Would you share a bit about how Scroll is different from the other technologies, and why do you think Scroll it's something that we should check out on?
Yeah. So this is always a difficult question to answer, and for 2 reasons. One, like, any comment I make, I'm not trying to throw shade on these other teams, right? I'm not trying to say bad things about them. They're all, I think, full of brilliant engineers and non-engineers doing really good work. And I think everyone in the space is wanting to push the ecosystem forward. So that being said, I think we all have our kind of different approaches and biases for how to do different design trade-offs. And I expected this to be asked, so I prepared a slide here. And to be honest, like, I am not designing and building this protocol, and so I might get nuances here wrong. And if anyone tells you I'm wrong, trust them and not me here. But the general idea is that Scroll and Polygon Hermes, which is now actually called Polygon zkEVM, you are writing Solidity, and it's going to be kind of compiling down the bytecode. And in both of these, this bytecode is equivalent with this EVM, right? So again, like I mentioned, all your tooling, all your tutorials, all your everything else, it's going to, all that bytecode that gets created out of your Solidity is going to look the same as it would on Ethereum and mainnet. Starkware and zkSync are different. And Starkware, you're going to be working in Cairo. I think there's this kind of like Solidity that can get cross-compiled to Cairo. And so it's kind of just like a different ecosystem overall. And we could probably call that more like a zkEVM going on. And then zkSync, you have, it is, they call it language compatible. So you can still write Solidity, but it's not being represented in the same way at the bytecode level. It's not like when you get out into the machinery of it, opcode by opcode is not going to match what you see on the EVM like you do in Scroll or Polygon's project. So that might introduce different security assumptions, right? If you've already written a smart contract for mainnet, you might need to re-audit that in the context of zkSync, or maybe you might have unexpected things in that transition layer. I haven't seen reports that has happened. I don't know if auditors have told people that they have to do that, but that's kind of one of the value props that might be a little bit different. I think the thing that really, for me, I think sets apart the Scroll team and why I'm so excited about it is really the emphasis and the like necessity around this decentralized prover network, and then eventually the decentralized sequencer. Those are the big things that I'm super excited about in our roadmap, and getting that hardware acceleration going so we can really get a robust network with lots and lots of participants beyond just Scroll, right? So
yeah, I agree that decentralization roadmap is something that I think all of the layer 2s are striving to achieve. And I don't think there is a single, how can I say, like a single consensus as to what decentralization is roadmap that someone's going to use. Probably Starkware to me seems like the closest to achieving that. I could be biased again. do you have any insight on like maybe some plans? Like it doesn't have to be like concrete, but what are the talks behind decentralization for Scroll? What are the ideas?
Yeah, so I think I'm still. Hopefully, I'm still sharing my screen, so I'm not just
Yeah, you
like.
are. No, yeah, don't worry about it.
Okay. Yeah. So like if you come back to kind of this view here, I was talking about the decentralized prover network. And so one aspect is like that, right? You can participate if you have this like a little bit beefy machine with a GPU. You can kind of like allocate your resources to be selected by the coordinator to make these proofs. And I think that's the closest on the roadmap. But then there's also going to be a challenge of decentralizing the sequencer. I've been to various talks internally about the like latest research of what we're going to do there. I hesitate to like speak about it in a recording because I don't know which one's the latest and I don't want to like put out wrong information. So
That makes a lot of sense. And
yeah.
thank you for trying to share. And I know it's it's putting you on a tough spot. It's a bit of a cheeky question by me. Sorry about that. We have one more by Lala. He's wondering if, let's say, because in Circom, there's this thing called a verify.so file, which is normally very expensive to execute on mainnet. Well, we know. So he's wondering if that were to deploy on Scroll, would it be much cheaper to try to verify Circom proofs, Graph16 proofs generated by Circom circuits?
That's interesting. I think, yeah, I mean, essentially you're looking at like a layer 3 where layer 2 is your Scroll and layer 1 is, Ethereum at that point. And that's definitely, no one's tried it. But yeah, if you have cheaper computation costs on your L2, then that's going to translate as well. That being said, I don't know what the Graph16 opcodes being heavily used are. And so those might be charged more gas if they're hard to do in the zkEVM context. But if that's something you're actually wanting to try out, get in touch. We like to do weird experiments or help developers do experiments. And I know we're also have been talking about, what precompiles can we offer developers so that, we're super excited about hopefully building an applied zk ecosystem within Scroll because we're excited about the field, right? So I don't know. It seems like that would be a fun project to work on.
That's fantastic because you mentioned precompiles, which is something that I also want to ask. Graph16, from what I understand from the code, uses some pairings and ECDSA, some elliptical curve add multiplication and add. So I wonder if I know that this is another tough question, so you don't have to answer it. But have those precompiles been supported by Scroll? Or
yeah, so we.
Or if you can't say it, probably that's a way for us to find out later.
Yeah, and we're not. I'm like 99% sure on our testnet we're not exposing any of those things as contract addresses that are precompiles.
Mm-hmm.
So the answer is going to be no at the moment. Mm-hmm. But later on, I'm not sure. And then also, like, I think one of the differences here, I can say a wrong thing because zero knowledge is not actually my expertise at all. So, I don't know what that looks like to have that support for something like Graph16 when our proof system is actually using like a KZG commitment scheme. And mm-hmm. So as those things switch, I don't even know if that's going to be something easy to bring in, but I know we do also have like ECDSA circuits, so maybe there's spaces there where some of those things can be optimized and other ones don't need to be. But
cool, excellent. So Lala, if you really want to find out, just deploy one on Scroll and see if it works. If not, I'm pretty sure Scroll is more than happy to get in touch, and probably you guys can collab on in that area. What do you think, Daniel?
Yeah, absolutely. Like literally, let me put this back up. This is actually my Twitter and my Telegram. So if you want to send me a Telegram at DG Helm, I'll get you connected with someone that can better answer your hard ZK questions. So
sounds fantastic. And well, we don't have any more questions. And again, thank you so much for everything that you have given us to the local community. I think that's the end. Like, do you have any last words to say, Daniel?
No, thank you. Thank you for giving me the time. And I hope someone will follow up with me and show me some of the best hacks from the mini hack, because that's always fun too.
Oh yeah, I'll keep you updated on our Telegram group. Don't worry about that.
Cool.
And all right, last words from me. Thank you so much, Scroll, for being a sponsor for our KL Mini Hackathon, and also willing to come by as a guest speaker. It's late in Daniel's time, so everyone just put an emoji, a clap emoji, or like thank you to Daniel. That would be very, very much appreciated. And I'm gonna stop recording, and I'm gonna share a bit of like final briefings on the KL Mini Hackathon, on what is to happen.